We're going to be doing an overview of OSPF, the different tables OSPF uses, how it gets a router ID and what that router ID is for, how it goes about establishing neighbor relationships, and troubleshooting the establishment of neighbor relationships. If OSPF is not able to establish a neighbor relationship with the router, it will not exchange routing information. And then the Dijkstra shortest path first algorithm, how that functions and what that's used for. Let's take a look at this diagram. For OSPF to function, we want OSPF to run here. And what OSPF is going to do for us, it's going to have all these routers talk to each other and share the information of their directly connected subnets. So router B here will share the information of subnet 99.16 and subnet 99.40 with router A. Router A will share its information with router B, router C, and eventually each router will know about each of the individual 5 subnets in this diagram. So to get this to function appropriately, we're going to need to do some certain things to make sure that OSPF will share this information. So when we go in and enable OSPF on each router, what we do is we type in router OSPF and then what's called a process ID number. This number does not have to match on each router. All it is a number that allows the router to keep track of this particular instance of OSPF on its router. There may be situations where you might have more than one instance of OSPF running on your router. The individual number allows the router to keep track of each instance. So I could do router OSPF 1 here, router OSPF 10 here, router OSPF 30,095 on router C if I wanted to. I probably won't do that. It doesn't hurt if I use the same number, so I usually use the same number just to keep it simple. So I go router OSPF 1. Now the next thing I have to do is I have to tell it what interfaces I want it to route for. And we'll get into that in more detail in another video, but real quick I'll do what's called publishing the interface. And I type in network 99, and I'm going to have all interfaces be in it, 99.0.0.0, and I'll use what's called a wildcard mask. Now the wildcard mask tells the router what parts of this line right here, what parts of this address has to match up against the IP address on the interface. So if I have an IP address of 99.32.0.1 on this interface and an IP address of 99.8.0.1 on this interface, the wildcard mask will compare the IPs on the interfaces of the router with this statement. So by having a wildcard mask of 0, 255.255.255, what that means is when it goes in and compares, it says, okay, 0 means the IP address on the interface, I'm comparing with this interface right here, must match what's in the first octet of this statement, which is 99. Is that a 99? Yes, it is. The 255 means it doesn't matter what's in the second octet. 255 means it doesn't matter what's in the third octet. 255 doesn't matter what's in the fourth octet. So the only spot that it has to match is where this 0 is, which is in the first octet. So it says any interface with an IP address that starts with a 99 is going to apply to this statement. So I've cleaned this up a little bit so we can actually read it. So to reiterate one more time, the 0 means it's going to compare the first octet of this address I put here, which is 99, to the IP addresses on the interfaces of the router. Each of the IP addresses on the interface of the router have a 99, so that matches. What the 255s tell it is it doesn't matter what's in the last 3 octets. So as long as the IP address on the interface starts with a 99, it's going to match this statement. And what this statement says is, I want the IP addresses or interfaces with an IP address that start with a 99 to be in area 0. OSPF is sectioned off into areas. And what an area does, it allows the OSPF protocol to minimize the amount of routing information that needs to go to every router in the network. Area 0 is always your backbone area. In the video, Areas with OSPF, we're going to go in and take a further look at configuring OSPF with multiple areas and the importance of areas. But the key thing here is we're just trying to get a look at how OSPF is going to establish neighbor relationships and what it does to exchange topology information. The first thing is it only establishes a neighbor relationship with the router that has an IP address on the next hop in the same area. So this interface is in area 0, this interface is in area 0. And if I want router A to exchange routing information with router B, this interface has to be in area 0. So I would do a similar command on router B. Now, once I specify the area information, OSPF, and I turn it on, OSPF is going to start sending out these hello packets. These hello packets are ways that the OSPF protocol uses to have the routers be friendly with one another. This is how they make their friends, and they only exchange routing information with their friends. These hello packets are going to go out every 10 seconds by default, and there's a dead interval of 40 seconds. So after 40 seconds of not hearing from their friend, they get really worried and that they think that that particular route is down. The information in these hello packets is very important, and it's got to match up. There's a subnet mask. The subnet mask doesn't match. They're not going to share with each other. The subnet ID has to match. And that goes with pretty much any protocol, though. If the subnet ID or the IPs aren't right, they're not going to share information. You won't even be able to ping. So they've got to be able to ping each other. The hello interval must match. Again, 10 seconds by default. That can be changed at the interface. The dead interval is always 40 seconds. Well, not 40 seconds. It's always 4 times the hello interval. So if I change the hello interval to 20 seconds, then the dead interval would be 80 seconds. So whatever the hello interval is, it's 4 times that for the dead interval. And then the OSPF area ID must match. So if I want all these routers to share information with each other, the interfaces that match up with each other have to have matching area IDs. So this interface has to be in the same area as this interface. After comparing their hellos, then the routers determine that they like each other as long as all that hello information matches. Then they will start exchanging topology information. And what they do is they exchange what's called a topology database. And what it is, it's all the information that they've collected to figure out how the network looks. So they kind of get an idea of how everything is connected based on the information they get from their neighbor routers. They do a full topology database exchange. Now, they use what are called database description packets to describe what the database looks like. And again, they're just trying to get a picture of the network. That's not the way that a distance vector protocol works. Link state protocols carry this topology database and get an actual picture of what the network looks like. RIP, IGRP, distance vectors, they don't care. They just discard information that they don't use, and they just take the best path that's available to them at that time. Once they've built this topology database, OSPF then uses what's called the shortest path first algorithm, math stuff. And they run this algorithm against the information in the topology database. That's how they determine what the best cost path is. Once they've determined the best cost path by running this shortest path first algorithm in the topology database, they put the best cost path in their routing table. And they store the other information. So that's why OSPF is CPU intensive, because it has to store this information and run this complicated algorithm against this database. to determine what the best cost path is, but it gets a really good idea of what the actual best path to take from one destination to another would be. So they've got a topology database, they've got a routing table, and they've got a list of friends that are directly connected that they share this information with. Now, the router ID is what they use to identify their friends. Everybody has to have a name that they go by, and OSPF uses a router ID as its name so the friend can identify the neighboring routers based on this router ID. So it has something to refer to the other routers with. Let's take a look at how these get their router ID. I've cleaned this slide up a little bit, and let's go take a look at how the routers get their router ID. Now, the router ID is determined by an IP address on the router. The router determines its own router ID. What it'll do is it'll look for the presence of a loopback interface. A loopback interface is an interface you can use basically kind of for management purposes. What it does, it allows you to have an interface that's not applied to a physical interface. So this is more kind of like a logical interface, and it's something that you can actually even ping and always test connectivity. So if you can hit the loopback interface, you know at least one of the interfaces is up on the router and something's functioning there. You can also use it for monitoring purposes, things like that. So a loopback interface, if it's there, is a management interface, and the highest IP address on a loopback interface would become the router ID. If there is not a loopback interface present, the highest IP address on an up and up interface will become the router ID. So in all neighbor tables, it'll have the same router ID representing that router. And again, the key thing is here, up and up. If the interface is not up for layer 1 and layer 2, it's not functioning, then it will not use that IP address as a router ID. So the router ID for router A, since this is the highest IP address it's got, would be 99.32.0.1. For router B, the router ID would become 99.40. This is .1 here, .2 here. It'd become 99.40.0.1, and router C's would be 99.40.0.2, because that's the highest IP address on router C. So in router C's neighbor information, it'll have a neighbor of 99.40.0.1, and in router A's neighbor information, it'll have a neighbor of 99.40.0.1, because it only uses one router ID. You could also use what's called a router ID command and specify the router ID if you wanted to. But it's nothing that needs to be done. If you just let the router do its thing, it'll take the highest IP address on an up and up interface and use that as its router ID to identify itself to the neighboring routers. Let's take a look in the simulator. I've got 3 routers configured just like this in the simulator, and we'll go in and look around for a minute. So on Palestra 1, if I do a show IP OSPF neighbor, it shows me the neighbor ID 99.40.0.1. It doesn't show me the next hop address as the neighbor ID. This is the next hop address. This is the neighbor ID. That ID will represent router B in all of its neighboring routers, neighbor tables. So if I look at Palestra 3, show IP OSPF neighbor, it'll show me the neighbor ID of router B, again 99.40.0.1, and it just happens to be the next hop address on this one. So what I would do is, if I did a show IP OS or show IP route, and I wasn't seeing the O's in here, O means OSPF. If I did not see the O's in here, what I would want to do first is figure out whether or not the OSPF process is establishing neighbor relationships. So I would use this command, show IP OSPF neighbors. And it shows me that there's a neighbor. If there is not a neighbor, then I want to go through and check everything. I want to take a look at the interface that I'm running OSPF on. And I see serial 0, I check to make sure it's up, the line protocol is up, and I would look at the IP address, 99.40.0.2 with a /13 subnet mask. What I would do is I would do show CDP neighbors detail command and take a look at the neighbor router IP, 99.40.0.1, and I'd make sure that they were compatible. If I had to, I could even telnet into Palestra 2. It's not. Oh, I haven't set password yet to telnet, so I'll do it the cheater way. I would do show interface and check out the IP address, or show run, and I would look at this interface right here. Serial 1 is the interface on Palestra 2 that connects to Palestra 3, and I'd look at the IP address, 99.40.0.1. Notice /13. Remember, if the subnet masks don't match in the hello packets and the IPs aren't sharing the same subnet address, then you're going to have problems. Also, I can't have the same IP. If they were both 99.40.0.1, I'd have an IP conflict. So I got to make sure that the IP stuff is fine. Once I've verified that the IP information is fine, I would check one other thing. I would use the show IP OSPF interface command. Because remember, if the hello information isn't right, then they're not going to share information. They're not going to become neighbors, all that stuff. So they have to agree on everything. They have to agree on the subnet, the IP scheme, hello interval, dead interval. If they disagree on any of that, they're not going to be friends with each other, and they're not going to share the information. So it's very important that they get along. So again, I can check the IP here, and you could actually use this command to check the IP subnet mask, hello interval 10, dead interval 40. And I want to check that on both routers to make sure it all matched up. So what I'd do is I'd go back over to Palestra 3 and I do show IP OSPF interface. And I'd check it out over here. Serial 0 is the one that connects to serial 1 on router B. IP, they're not the same, but they're compatible. Subnet mask is the same. Hello ID is 10. Dead interval is 40. Priority, we'll talk about that a little bit later in the next video, actually, with designated routers. But the key information matches, so they're able to become neighbors. So once I've verified that, again, show IP OSPF neighbor, and if everything matches up, you should see the neighbor router in this list of neighbors. And what this state means, full, is it means they have fully exchanged all of their topology information, and then the router was able to run its shortest path first algorithm on its own topology database and figure out what the best path to put in the routing table is to get to the particular destination subnets. So let's do a quick recap on the troubleshooting of these neighbor relationships. Now, the first thing you're going to do, and why we want to troubleshoot these again, is if we're looking in our routing table, we do a show IP route, and we're not seeing any O's. We want to see some O's in there. O's stand for OSPF. If we don't see them, then we want to go in and we want to check some things. First thing I might do is show IP OSPF neighbor and see if I've established a neighbor relationship. If I have not established a neighbor relationship with the router I'm assuming I should be able to establish a neighbor relationship with, I'll make sure that my interfaces are up and up. I'll start with just layer 1. If this is up, that's layer 1. If this is up, that's layer 2. That's good. I'd verify the layer 3 information, making sure the IP addresses are correct. Remember, if the subnet mask does not match, or there's a problem with the IPs, they will not establish neighbor relationships. So all layer 1, layer 2, layer 3 has to be good. On top of that, I need to go in and verify the hello and the dead interval. By default, the hello interval is 10 seconds. and the dead interval is 4 times the hello interval, so that's a 40-second default. I can use the command show IP OSPF interface. That will allow me to view the IP addresses as well as the hello and the dead interval. Again, this is very important because if these guys don't agree on all of this information and it doesn't match, then they're not going to establish that neighbor relationship. They're not going to share their topology information with each other, and the routing tables will not get populated. I would also verify the area set for OSPF. If the interfaces on the neighbor routers, so this interface right here and this interface right here, if they are in different areas, they don't like that. So they won't share information then. So they have to agree on all of that to establish this neighbor relationship and share that topology information. And again, what's in that topology database is used to calculate the routes with that shortest path first algorithm. So again, it goes in, calculates the best cost path based on the information in this topology database. So it all hinders on this show IP OSPF neighbor command, making sure that the neighbor relationships are there and all this information matches. If it doesn't match, then it's not going to function. So we have done an overview of OSPF. We've talked about the tables, the topology table, the routing table, the router ID and what that's for, the process of establishing neighbors. And again, if the router is unable to establish a neighbor relationship, it's not going to exchange routing table, not going to be able to route. Troubleshooting those neighboring relationships as well as the Dijkstra SPF algorithm.